So, all right, objective 3, we want to find products and quotients of complex numbers. The exponential form of a complex number is useful for finding products and quotients of complex numbers since we can use the laws of exponents. So our theorems here state that if suppose z sub 1 is equal to r sub 1 times e to the power of I times theta sub 1, and z sub 2 is equal to r sub 2 times e to the power of I times theta 2 are two complex numbers. So then essentially we can rewrite z1 times z2 is equal to r sub 1 times e to the power of I to times theta sub 1 times r sub 2 times e to the power of I times theta 2. This just simplifies down to r sub 1 times r sub 2 times e to the power of I times the sum of theta 1 and theta 2. So these are really just the ones to remember there. Then we have that if z sub 2 is not equal to 0, then if we divide z sub 1 by z sub 2, we end up getting r sub 1 times e to the power of I times theta sub 1 divided by r sub 2 times e to the power of I theta sub 2. Which then just simplifies down to r sub 1 divided by r sub 2 times e to the power of I times the difference of theta sub 1 and theta sub 2. So once again, this last part of our theorem there is going to be the most important part. So for example 3, if c is equal to 3 times cosine of pi over 9 plus I times sine of pi over 9, and w is equal to 5 times cosine of 5 pi over 9 plus I times sine of 5 pi over 9, we want to find the product and the quotients. We want to find z times w and z divided by w. Then we want to express our answers in polar and exponential form. All right, so definitely some parts we're doing. So we're going to start with A. So if we start with A, we're multiplying z and w. We know what all of our values are going to be. So we can go ahead and we can use equation 5 there. So we can determine that our rate 1 is going to be 3, our rate 2 is going to be 5. E and I are going to be the same. Theta I is going to be pi over 9, and theta 2 is going to be 5 pi over 9. So we can replace everything from equation 5 here. So z times w is going to end up becoming first, it will be 3 times e to the power of I pi over 9, then times 5e to the power of I times 5 pi over 9. So then simplifying using that last part of our equation there, this is going to end up being simplified to 3 times 5 times e to the power of I times the sum of pi over 9 and 5 pi over 9. So pi over 9 plus 5 pi over 9. And now we simplify. So 3 times 5 is just 15. Then we have e to the power of pi over 9 plus 5 pi over 9 is going to give us 6 pi over 9, which simplifying gives us 2 pi over 3. So we have I times 2 pi over 3. And this here, this is in our exponential form. Remember, we want our answer in polar form and exponential form. So we'll put this into polar form. Very easily, we see that our value of r is 15. Our theta value is 2 theta over 3. So we plug that in fairly easily to get r times, remember, cosine of theta, so cosine of 2 pi over 3, plus I times sine of 2 pi over 3. And this here is our polar form. So now for part B. Now we're finding the quotient. So we're taking z divided by w. If we have z divided by w, we want to put this in our first version of our form here. So we end up getting 3 times e to the power of I times pi over 9. Now all divided by 5 e to the power of I times 5 over 9. Then we end up with our rate 1 divided by rate 2, so we end up with 3 divided by 5 all times e to the power of I times the difference between theta 1 and theta 2. So we're going to end up taking our value of pi over 9 minus 5 pi over 9. So when we simplify this, we'll end up getting 3 over 5 times e to the power of I times negative 4 pi over 9. But you see theta has to be between 0 and 2 pi. So we need to end up adding 2 pi to negative 4 pi over 9. And this is to get in range. So this is really going to be equal to, let's put this over here, 3 over 5 times e to the power of I times negative 4 pi over 9 plus 2 pi, which then gives us our value of 3 over 5 times e to the power of I times 14 pi over 9. And remember, this is our exponential form. So let's pull this down just a tad. And we found our exponential form first, so to find our polar form, we know that r is going to be equal to 3 over 5, and theta is equal to 14 pi over 9. So in our polar form, we'll end up getting 3 over 5 times cosine of 14 pi over 9 plus I times sine of 14 pi over 9. And that will be our polar form. So, all right, quite a few things are definitely solidifying how to go from polar form to exponential form. We saw how to multiply and divide different complex equations there. Then we also had that from this example, we get that the argument of a complex number is going to be periodic. So that means that if we have r times e to the power of I times theta, this is then equal to r times e to the power of I times the sum of theta and 2k pi, where k is an integer. So that means that even if we do go forward to pi, we would have the same value as before. We do see that this is going to be periodic because we do also use the values of sine and cosine, which are periodic functions. Objective 4, we want to use de Moivre's theorem. So in its most basic form, de Moivre's theorem is a formula for raising a complex number z to the power of n, where n is greater than or equal to 1 and is an integer. So our actual theorem for de Moivre's theorem is that if z is equal to r times e to the power of I times theta is a complex number, then z to the power of n is equal to r to the power of n times e to the power of I times n times theta, where n is greater than 1 and is an integer. So really we're just using this theorem to go ahead and state what our complex number z would be if it was raised to a specific power. So example 4, we're going to express 2 times cosine of pi over 9 plus I times sine of pi over 9 to the power of 3 in exponential form r times e to the power of I theta, and in the rectangular form x plus yi. So we want to use de Moivre's theorem. And when we do, we see that z is equal to 2 times cosine of pi over 9 plus I times sine of pi over 9, which means that 2 times cosine of pi over 9 plus I times sine of pi over 9 is going to the power of 3 is then equal to z to the power of 3. So we can use our de Moivre's theorem now. So, this is all to the power of 3. There we go. So if we raise this all to the power of 3, 2 to the power of 3 is going to be 8. So we have it in our form of r to the power of n times e to the power of I to the n theta. So we have r to the power of 3 to the power of 3 times e to the power of I times 3 times theta. So in this case, it'll be 3 times pi over 9, which ends up just giving us 8e to the power of I pi over 3. And this is in our exponential form. So we have our answer in exponential form, but if we want to get to rectangular coordinates, we have to go to polar first. So in our polar form, this would end up being z is equal to 8 times cosine pi over 3 plus I times sine of pi over 3. So now we have these values. Remember, we want to put these back in rectangular coordinates. So we're going to find the values of cosine of pi over 3 and sine of pi over 3, which then gives us 8 times 1/2 plus I times the square root of 3 over 2. Simplifying this value, 8 times 1/2 is just 4. 8 times the square root of 3 over 2 would end up being 4 times the square root of 3 times I. And this here is in our rectangular coordinates. So these are in our rectangular coordinates, but just to reiterate here that our exponential form, 8e to the power of I times pi over 3 is equal to our polar form of 8 times cosine of pi over 3 plus I of sine of pi over 3 which is then equal to our equation in rectangular coordinates, which was 4 plus 4 times the square root of 3i. So just remember, even though they are in different forms, they are all equal. All right, last objective, objective 5, we want to find complex roots. If w is a complex number and n is greater than or equal to 2, then a complex number z that satisfies z to the power of n is equal to w is a complex nth root of w. If n is equal to 2, the solutions of z squared is equal to w are complex square roots, and if n is equal to 3, then the solutions of z cubed equals w are complex cube roots of w. So in order to find complex roots, we suppose that w is equal to r times e to the power of I theta is a complex number and n is greater than or equal to 2 and is an integer. If w does not equal 0, there are n distinct complex roots of w given by the formula z sub k is equal to the nth root of r times e to the power of I times 1 over n times theta plus 2 pi k, where k is then between 0 and n minus 1. So let's do an example. We're going to find the complex roots of -1 plus the square root of 3i. Then we're going to express the answers in exponential form. First thing we want to do is express this in our exponential form. Since we want to use our equation, this means we need our exponential form there. My cat will just a little. So we have -1 plus the square root of 3i. Putting this in our exponential form, we get that this is going to be equal to 2 times -1/2 plus the square root of 3 over 2i. Remember, we can't just go straight to exponential form. We have to go to polar form first. So we have to really work backwards in this case. Then the only values that would then make this true would be 2 pi over 3. So we have 2 times cosine of 2 pi over 3 plus I times sine of 2 pi over 3. So this is in our polar form. So since we now have it in polar form, we can put it in our exponential form, which is now just going to be 2 times e to the power of I times 2 pi over 3. It's our exponential form. All right, so now that we have our exponential form, we want to use equation 7 to go ahead and find. We're going to go with 3 complex roots. So we're going to use equation 7 to find 3 complex roots. -1 plus the square root of 3i. If we want to find 3 complex roots, let's go ahead and do k is equal to 0, 1, and 2. Our equation for if we were just finding z of k is going to end up being the third root of 2 times e power of I times 1/3 times 2 pi over 3 plus 6 pi k over 3. That's our plus 2 pi, but we've changed it so now it has a denominator of 3. And k is equal to 0, 1, and 2. So this is going to give us that z of 0 is going to be equal to the cube root of 2, 2, times e to the power of I times 1/3 times 2 pi over 3 plus 6 pi times 0 over 3. So simplifying this now, we still have our cube root of 2 times e to the power of I, or 6 pi times 0 over 3, that's just going to be 0. And we have 2 pi over 3 divided by 3, which gives us 2 pi over 9. So let's do this now for z1. So we have the cube root of 2 e to the power of I times 1/3 times 2 pi over 3 plus 6 pi times 1 over 3. So this is 6 pi over 3. So 2 pi over 3 plus 6 pi over 3 is going to give us 8 pi over 3. 8 pi over 3 then divided by 3 will give us cube root of 2 times e to the power of I times 8 pi over 9. And lastly, our last cube root here is going to be z sub 2. So we have the cube root of 2 times e to the power of I times 1 over 3 times 2 pi over 3 plus 6 pi times 2 over 3. So now I have 6 pi times 2, which is going to be 12 pi over 3, plus 2 pi over 3 is 14 pi over 3 divided by 3, which then would end up giving us the cube root of 2 times e to the power of I times 14 pi over 9. So if we wanted to find 3 complex roots, that would be a formula then, and then here would be our 3 complex roots, or those first 3 complex roots. Expressed, of course, in our exponential form. All right, that finishes up our section 9.3 for today, and I'll see you again in section 9.4.